I am going to call for Bowerk at this time. So.
What's up, kids? Oh, you're gonna throw the bell? You're gonna throw in the bell?
All right.
So they're all
Don't
right
throw.
there.
Don't throw.
Don't throw.
Don't sell. Don't pull.
Everyone I checked
See,
did
look.
pretty well.
This is sign back. This is side 500. This they're expanding.
You guys can
So in other
you
words,
just one.
sign
Your cost is one.
5x.
Someone knew it wrong. Yeah. Someone got this.
This and this added, which is this.
It's
That's why they give us the expansions. That's this.
AS chemistry's got everything right so far.
And then your always says, "Oh, you suck. You guys don't have enough."
Then you go by two to get.
It's like basement. It's basement.
I have a but I will not say that. All right. Look at
This wasn't it?
it's for Kaylee.
Yeah.
Beller to on you today.
It's on the house.
One mark. You get some marks for the class. Let's see.
It's 5.
One mark. Right there. All right, one mark.
I think it's.
All right, we're gonna go over the answers.
They're saying like 1 out of 5. So they got really worried there.
Oh no. One mark for the class.
Anyway.
Alrighty, so let's go ahead and go over those answers so we have them. And then we'll get on to today's lesson and the schedule for what's happening. So, here we go. KSP expression, pretty simple, 2 marks here. Nickel 2 plus. IO3 minus. So what exponent? So the second. Units, mole 3 cm minus that. This is gift marks. Why? This is 1 and this is 1. Not all marks are built the same, recall. There are 2 mark questions that require a ton of math. And then there are 2 mark questions that could be like this. All right, so then the next one is to calculate the numerical value of KSP. I just did it this way. KSP equals x plus u, 2x squared. How many of you are just going straight to do that? If you're not, then you're doing this, right? Nickel plus 2 plus 2IO3 minus, and you're setting up your equation. We don't know what this is, but we know that we're getting rid of it because we're finding out how much is soluble. This starts at 0, this starts at 0, this is plus x, this is plus 2x, x and 2x, right? And then x is going in here, and 2x is going in there. That's how we get here. So then we have x, we have it, it's this. That's it. So then we just plug in. I usually just do the math and I have 4x cubed. I plug this in for x. And the answer is 4.87 times 10 to the negative 5. The math was worth 1 mark. Bless you. All right, I'll pause. Bless you. On the next page, I have one. Yes, Ramon.
So you don't have to include the units in the KSP, right?
They didn't need it because they asked for it here.
Okay. So
So
if they
we-
asked for it before, like,
I mean, here. Yes. Are you guys arguing over the game? Yes. They're play testing a game that I found in the secret laboratory software. All right, so Bowerk 2. This is actually very similar in its structure. Magnesium benzoate is pretty much the same thing that breaks apart. And they gave you the KSP here. They're telling you this is X and then this is once again 2X. So you would get KSP equals x times 2x here. KSP equals 4x cubed. The equation is the same as the last one. You don't get any marks for the equation, but just in case you wanted it, mg plus 2, or mg, all this stuff. Benzoic acid, mg plus 2, so C6H5 2OO minus 2 of those, 0, 0, plus x plus 2x, and that's what's going there. Then we plug in which thing here. We have the KSP. So we plug in the KSP, yes, that's all.
Since when was the amount of moles, like both the coefficient and the exponent?
Since
In the-
every ice table has always been like that.
Okay, I've been doing that one this whole time.
Every ice table, because when you are making one magnesium 2 plus ion, you're making 2 of this other ion. So you have to consider that for your equilibrium amount. And then for your formula, you have to use this for just your standard equilibrium formula for K. It's always products over reactants. But technically, it's products like A to the X, B to the Y, where X and Y are the coefficients. Every equilibrium is done like that, where these numbers right here are the coefficients from your balanced equation. That's why you're seeing it count twice. The 2 in here and the 2 up there. And so then we have our KSP is 1.76 times 10 to the negative 7 equals 4x cubed. And then we solve for x. If you solve for x correctly, you'll get 0.00353. And if you got this answer, this was worth 1 mark. That was 1 mark. The second mark is to change this mole DM minus 3 and to change it to grams. So this is mole DM cubed. And then to change the grams, you would do 1 mole is its molar mass. Molar mass here is 266.3, which you have to multiply. That's what cancels the moles. Or just use the formula, multiply by the molar mass. And your final solubility was 0.94. If you got 0.94 or 0.940, you got the answer correct here. And so that's what we did last lesson, which was lesson 5. Today, lesson 6 directly correlates to lesson 5. It's another topic within KSP. So you'll still need to know how to create these equations. We're going to go over how to today. And beforehand, though, I'm going to go over some class updates. So I'll pause because some people are still writing about work and go over class updates. First off, for those of you that are interested in participating in the chemistry Olympiad this year, the Olympiad is not until March. It's usually like the first week of March. However, I thought, because there is some interest in it and some people did participate in it last year, that I would tie some extra credit into the A-level class for those students that want to participate in the Olympiad. So I created over the weekend a practice set of Olympiad questions that are related to the unit that we are in right now. Some of them are direct questions with KSP, with KA, weak acids, buffers, and some of them require a little bit more knowledge than what is in the Cambridge curriculum. But some of you have asked for the AP books, and I believe it will be in the AP books on how to solve some of those questions. So if you complete that practice set, and it's going to post on quizzes later today, I'm probably going to do it during lunch. I've already made it. I just have to post it. If you complete that practice set with the 80% or higher, then I will tack on an extra 5% to your unit exam grade. So does twofold, gives you a little bit of extra credit, a little bit of extra practice, and you're also getting to see the style of the questions on the chemistry Olympiad that are directly aligned with what we are learning right now. On top of that, for those topics that aren't in the Cambridge curriculum, but would be on the Olympiad, I plan to do some additional review sessions, basically more chemistry. And so I put on the schedule for Thursday of this week an ACS Olympiad practice number 1, that would be me teaching you a topic that's not in this curriculum, but would show up on the Olympiad, specifically hydrolysis. And so if you are interested, because I just want to know if I have enough interest, if you're interested in coming on Thursday and doing some Olympiad practice, raise your hand so I know if, okay, perfect. I just needed, 4 more and I'll run the practice. I already kind of created it, but just to know that there is interest because I'm investing additional extra time in creating these resources and creating like basically extra lessons, extra chemistry that's outside of the scope of the Cambridge curriculum. So that's going to happen on Thursday. See, it's on the calendar over there. It's a busy week for me, but I did want to provide you with that source. And then what I can do is once per unit, we'll do the same thing throughout this year. Whatever that unit is, I'll put a practice setup that's ACS Olympiad related that goes into the same topics, but how would it be worded there? Do 1 review session per unit, do an extra credit. And that's how we'll run some additional extra credit in this class. Sound good? Yes.
That's after school, right?
After school Thursday. I don't have another time. Because like, I don't have an open period.
Because like, if it was like during lunch. Right.
Yeah, I have to not teach for like a few minutes at least. Because remember, I don't have a planning period, so I have to eat. Or I will crash out. Especially this week, because we were here till 8 p.m. last night. All right, make sense? All right, so I wanted to bring that up. On that note, it's been on the calendar for at least a week. Your Unit 1 exam is approaching. Today is the last lesson of the unit, meaning next Monday is your test. So next Monday is your first exam in this class because you haven't had a test yet. So next Monday, just a reminder, that means you bring your workbooks that day, you drop them off, I grade them, and then you'll be taking the exam. The exam will take the majority of the class period because it's A level. And then it generally does take a long time to get through the exam because you've got a lot of math that you'll be asked to do. So I will probably do a bell work that morning and then go straight into the test after that. But once again, that's going to be Monday morning, and that's a full unit exam going in the grade book. So make sure you study this weekend. Thursday will be a review day. So we'll be doing review activities that I'm putting together on Thursday to practice. We'll have a bell work. We'll do a couple of different reviews, and that'll be Thursday. So that's the schedule. Got a lot going on in this class. All right, so final lesson. Let's get to it. Unit 1, lesson 6. I am recording, yes, and plugged in, so it shouldn't go out. Today we're learning about something called the common ion effect on KSP. So these words, common ion, are going to show up a lot in today's lesson. There's one standard with 2 parts. And so it says candidates should be able to understand and use the common ion effect to explain the different solubility of a compound in a solution that contains a common ion. Whatever that means. We'll go over that shortly. My gloves are on because I'm going to show you in a demonstration along with what's up here. It says perform calculations. So we're going to need our calculators back out. Using KSP and the concentration of a common ion. And so once again, this is the final lesson for Unit 1. So the last topic I'm going to put on the test. So a week ago when we went over this, partially soluble salts, we said that HCl, for example, breaks apart, but it only breaks apart a very small amount. And we would define that amount as X, how much it breaks apart. And so if there's one of these and you start off with 0 of each of the ions, that the amount that breaks apart here would break apart equivalent, 1 Ag plus and 1 Cl minus of each of those. So we don't know what that X amount is, but we know that they're the same in this case as each other. And we would make ourselves a little ice table to help us figure that out. The X on this side doesn't matter. Why not? Like, it doesn't matter that we don't know what the starting amount there is. Go ahead. Because it's a solid. So it ends up not counting. So you only use this information to find out how much of your ions it breaks apart too. So on this slide, if you'll recall, I said typically all equilibrium constants are products over reactants, products that are raised to the exponent of their coefficient, right? But in this specific case, you cancel out the reactants because it's a solid, and that's for all KSPs. So it's technically just the products. And so we did a bunch of math with that. So now that's where we were at. Here's where we're going. Yes.
Why is that not
I don't know, probably because if that's silver nitrate, then he totally wants to have brown paints that are staying for weeks.
It could be water in the milk.
I mean, it could be, yeah. But if it is silver nitrate, I'm just saying. Anyways, common ion effect. So this is defined as a reduction in the solubility of a dissolved salt. So when I have a compound that has an ion in common with the dissolved salt, it's going to cause precipitation to occur. And it's a principle that is in line with something called Le Chatelier's. So I'm going to show you. First, I'm going to tell you, and then I'm going to show you because I have a demonstration that I put together. I was here forever yesterday anyways, so I had the time to put a little demonstration together. So first, let's talk about what it is, how this applies, why it ties into KSP. I'm going to show you. I have a demonstration at my table, and then we'll talk about the math afterwards. So this one right here is actually the demonstration I'm going to show you. If I have this equilibrium and I add a base to this equilibrium, what's going to happen is the reaction will shift to the opposite direction. So according to Le Chatelier's principle, my reaction will always shift to the opposite side of where I add additional stress. Stress could be added concentration, it could be added temperature, it could be added pressure to either side of the reaction, but we're only talking about additional concentration. And so this is the one I'm going to show you very shortly, actually. This is weak acid. If I add a strong acid in, same thing occurs. The reaction goes to make the opposite side. Equilibrium shifts to the reactive side. And so when I add, in this case, more base, or in this case, more acid, we actually call that the common ion effect, because that ion is produced in this reaction. And so we're going to take a look. I have a little demonstration here with that reaction. So what I'm going to do is these steps. That's the equilibrium. And so I have 3 beakers here, and it says add phenolphthalein to each beaker. So I'm going to add phenolphthalein. Hey, do y'all remember phenolphthalein?
No.
It might bring back some memories in a moment. Phenolphthalein has a pH change. Its pH change is at 9. It's colorless below 9, and it's hot pink above 9. Does it ring a bell now?
Is that one turning pink, or is that just like the tablet?
It might be my computer, but I can't change it because I'm recording. Okay, so I got some phenolphthalein going on. It might have some reservoir of something in it. And then what's the next thing I need to add? It says ammonia. So I prepared some 3 molarity ammonia, and I add that to each of these. Get me some hot pink going on. What does this tell me about ammonia? So I originally just had water in here, and then I added ammonia, which means basic. And then it says add NH4Cl to beaker 2. So right now, I have just added ammonia into water. I have not done anything else, which means that what I have produced from adding ammonia into water is NH4 plus and OH minus. So what's turning that color pink? The OH minus that's been produced as a result of adding ammonia to water. So now I have a sample of NH4Cl. I'm going to go ahead and add it to this one just because. So I'm going to add a little bit here. happened? But I added NH4Cl. Why did that happen? Why did the color go away? Go ahead, Isabella.
Maybe the solvent to hydrochloric acid and ammonia, and the hydrochloric acid reacted.
Remember, I'm right here, right?
I don't know.
I added this common ion. Do you agree? I added this NH4Cl. The chlorine doesn't matter. The NH4 plus is part of the reaction. So what happens when I add more of this? What happens? It reacts with the OH minus. The wording we say is it consumes the OH minus, the excess OH minus in the solution. So is it pink anymore? No, because the reaction shifted to make the reactants. And that's why the color appears. Le Chatelier's principle in action. So I did have something I wanted to test. Well, what if I had added NaCl to a beaker? So this was NH4Cl that I added over here. I saw the color disappear. What do you predict would happen if I added NaCl to a beaker? NaCl. Let's see. Some salt. Oh no, not my NH4Cl. That might have gotten in there, but I don't think so. Okay. So do you see anything happening? I don't see anything happening. Why not?
No NH4.
No common ion. So I can't just add any salt and shift that equilibrium. The salt must have a common ion. So this is called the common ion. And in insoluble salts, the same thing's going to happen. But when we shift this direction, what does that mean happens to the solubility? If we're shifting towards the solid, the solubility will decrease. And so that's what the common ion effect is. So I wanted to show you, demonstrate that to you, and then we're going to take a look at the math. So the color disappeared, right? And here, when I added NaCl, no common ion, color stayed the same. There was no shift. Because Na plus and Cl minus is not here at all. So it didn't affect this chemical reaction at all. Clear? Okay, so if we understand it conceptually, then we can hopefully understand it mathematically in a little while. So no change. All right, I'm gonna go ahead and continue. So what about the math? We're gonna get to how does the common ion affect the math. First, it says copper with bromide is a sparingly soluble salt. Calculate the solubility in pure water. This means no common ion. This means the same thing as what we've been doing the whole time in the last lesson. We're just going to take CuVr, we dissolve it in water. It doesn't dissolve largely in water. With this. Just like the bell work. How would we calculate the solubility? We call this X. So we're solving for X. And so now what? We get ICE. This doesn't matter, but we know the change is minus X, how much it dissolves. 0, 0, plus X, plus X. So you end up with, this is nothing, X and X. And I get 3.2 times 10 to the negative 8 equals X squared. Are we okay with that? Take the square root. I did the math. Just double check them. I get 0.000179 equals X. Or 1.79 times 10 to the negative 4 equals X. That's taking the square root of both X. That's our solubility. Mol Cm minus 3. Pure water. Nothing new yet. I believe the next slide is where we have something new. And so you're going to want to pay careful attention. Because the question is, how does the common ion affect the math to prove the point that I just went over and showed you? That happens. Let's do the math. Ready? Okay, so let's calculate the solubility of CuVr in a solution of potassium bromide. So how would we go about this? What alteration what would change? CUBR goes to CU plus BR minus. And this is why I suggested to make an ICE table, ICE. We still know this changes X. The starting amount of copper is 0, but is the starting amount of bromine 0? What is the starting amount of bromine? How do we know that? This is K plus 1, Br minus 1, so we do have to check that, right? That this compound only produces 1 Br minus, because that would matter, that would affect it. But it's 0.02 Br minus to start. Does that make sense? Because it's not in a solution of pure water. It's in a solution that has 0.02 molarity KBr. There is a common ion here in the copper bromide. That common ion is bromine. So then how does that affect the math? This is plus X. This is plus X. And now we have, this doesn't matter. We have this is X. And this is 0.0200 plus X. What does that mean? Go ahead.
When we get quadratics.
So what a wonderful question. Technically, what would your equation be? It would be KSP equals Cu plus times Br minus, and I would, if I was to put my math hat on, I would say, okay, so that's 3.2 times 10 to the negative 8 equals X times 0.0200 plus X. And most of you who are either in AS level math or A level math are going to start saying, oh my God, FOIL or distributes, you get a quadratic, you have to solve it with the quadratic formula because that's a 0.02x, because you're not going to be able to really solve that another way. And you're going to start freaking out. Cambridge said they will not make you use the quadratic formula in any question. How is that possible? To solve for x here, you would think you would need the quadratic formula. So is there something I told you, it's about 2 weeks ago, that you could do here? Lisa?
Maybe about the concentration being if it's too small to put it in. I don't know.
Yes. So I'm going to write here. If your K is 100 times smaller than the concentration, you can ignore x's that are being added to numbers. The phrasing we say for that is we assume x is small. You can ignore x that is added to numbers. The wording or the phrasing you may see for that is assume x is small. Well, will your K be very small in KSPs?
Yeah.
Will your K always be very small in KSPs? Yeah, it's barely breaking apart, right? So I would say if I was to compare 0.02 to 0.00000032, that this is less than 100 times smaller. Would you agree? So what does that do for us mathematically? Bye. Your math, go ahead.
It's right. I'm guessing we will have to use quadratics. It will be a big difference.
For a Cambridge exam, you will never have to use a quadratic formula. I've never seen a question in a Cambridge exam where they would require you to use it.
If we do,
I mean, yeah, you do.
You would be spending time, extra time to
will
solve.
we get marks for that?
If you approximate, because you would get an approximation of a very similar answer where x is small or not, you should still earn the full marks for it. I do believe if you have the Casio calculator, you can literally just plug your quadratic equation in and get the answer. So if you forget this, you should be able to do that, come across with it, as long as you said the whole thing equals 0 correctly. Yes.
So
Yeah, when it's x added to a number, you assume it's small, you forget about it, you say, we don't need it. But you can do that. You should try it and see how close your answer is to the answer that we get by assuming x is small. 3.2 times 10 to the negative 8 equals, this now becomes x times 0.0200. Do you see what I did? And now it's linear. It's not quadratic. Yes.
How do you say the CUBR was 3 again? If it matters.
Wait, which 3?
That's the 3 in the I for CUBR. That's a 3, right?
This number?
No, in the ice table.
This right here? Oh no, this is just me scratching it out.
Oh.
The whatever this is never matters because it's a solid. Solids equal 1. Every solid equals 1 no matter what. So then do 3.2 times 10 to the negative 8. Divide that by 0.02 on both sides.
I got 1.6 with the Casio.
1.60 times 10 to the negative 6 is the answer for x.
Yeah.
Yes, you can do it. Remember, the chemistry guidance is they will not take off marks if your chemistry is correct. And technically, in my more advanced classes, I would use the quadratic formula to solve questions. They have just stated that it is unnecessary to solve the questions using the quadratic formula. So they give these techniques to help you bypass quadratic formula. But if you have your math head on and you want to solve it with quadratic formula, you should come up with the same answer as long as you make sure you're only keeping a positive answer with with the quadratic formula, not the negative.
What if you really get positive?
Then you have to check them both and see if they go back in. But there should only be one positive answer. Yes. Jason, have you makers?
So like it's fine to like the idea was fine to just put that in here.
Mm-hmm. Because of this. This is the thing. And this was brought up in weak acids, that if you had a situation where you had a number and you added x, and I said it would become important later on. This is where it becomes important. If you have a situation where you're adding x to a number in an ice table, and x is, your K is 100 times smaller than the initial concentration, and clearly 0.00000032 is way more than 100 times smaller than 0.02. That's where you can make the assumption that x is small. Question: did adding this bromine into the solution decrease the solubility? This is the solubility of CuBr with the bromine in the solution. This was the solubility of CuBr without the bromine in the solution. Did the solubility decrease as the Chatelier's principle would say? Yes, it did. Which basically is just us checking ourselves that that makes sense. The solubility should be less in a common ion. Make sense? Kind of, sort of. We'll practice this more. Let's take a look at a Cambridge paper 4 question. So exciting. Table lists KSPs for some group 2 carbonates. Use the data in the table to describe the trend in the solubility of group 2 carbonates down here. So find your keyword, describe the trend. Describe the trend. Use the data to describe the trend. It says use the data. So how am I going to earn this 1 mark? What do I say?
Here's soluble down the middle.
It's less soluble down the group. Why? Or solubility decreases down the group. Less soluble down the group. Let's use the data. How do we use the data to say this? Because the KSP values decrease, they get small. That's all you have to say. You do not have to discuss anything else. They're not asking you to, but they're asking you to use the K values to explain this. Does that make sense? That the smaller the K value, the less soluble? Because we said this, right? K is more than 1, products favored. K equals 1, equilibrium. Equals products over reactants. K is less than 1, reactants favored. So the smaller the K, the more reactants are favored. In this case, reactants are what? Smaller K equals reactants favored more. And when we're talking about this reaction, we're talking about this. MgCO3 goes to Mg plus 2 plus CO3 minus 2. You can see that's down there. When I talk about K being smaller, I mean we're shifting more towards the salt, which means we're shifting towards being less soluble because it's more solid. Next one says write an equation to show the equilibrium. I just did that, showing like what I was talking about. So literally, equilibrium for the solubility product for MgCO3 includes state symbols. So what would be on my reactant side? The MgCO3. On the product side, Mg plus 2 plus CO3 2 minus. And what are my states of matter? MgCO3 is solid, and the others are? Thank you. You get a mark for that. It's worth 1 measly mark. So if you forget the states of matter, you have 0. If you write one charge incorrectly, you have 0. Where's 1 mark? Which means they expect this to be something you could come up with relatively quickly. It continues. We have more to this question. So 1, 2. With reference to your equation, what is observed if I were to take some Na2CO3 and add it to a saturated solution of MgCO3? So using the equation that I'm just going to rewrite it down, what would need to happen if I added some Na2CO3? Can anybody tell me what would happen? See if we can get those marks. Francesca.
The reaction will shift to the left.
The reaction will shift to the left, which means that's one of the marks.
The solubility
It means the solubility would do what?
increase.
Decrease. Because you're going to go this way, you're making more solid. That means less soluble, right? So the idea is that you're adding some extra common ion. You're adding more CO3 minus 2. So what this does, where the marks are, is adding CO3 2 minus, or you could say adding a common ion. That is the common ion. But adding the CO3 2 minus will shift equilibrium to the left, which decreases how much breaks apart? Because you're putting it back together is the idea. Staying in the solid, which decreases solubility. And so what would be observed? Because we haven't said what would be observed. And there's a mark for that. Go ahead.
More precipitate, so the
You have to say the color.
it was darker.
So, interesting. It says what is observed. Underline those words. Observed means what would you see in a lab? What do you see? That is a terrible eye. What do you see in a lab? Francesca. No, because MgCO3 would technically in saturated solution be colorless. What would happen if we're going that way? What do we see? Somebody said precipitate, but you actually have to give the color.
Is it white?
It's white. A white DPT would be observed. Why? Why is it white?
Like using carbonate white.
How do we know that? How do we know? I'm gonna write. How do we know this? Well, back in the day, I'm pretty sure I've mentioned it a few times, but I'm gonna say it directly. All salts, all ionic compounds compounds of group 1 and group 2 metals are white precipitates. Every single one of them. The only metals that get colored in compounds are ones that are deep block metals due to their electrons and their energy levels, which we will talk about in December. But at this point, how do we know this? All group 1, yeah, because ligands. All group 1 and 2 ionic compounds are white when not dissolved in water. They're all white. They're like sodium chloride. They look kind of like that. Yes? You should write that down. Because sometimes they ask you to observe, and that would be an observation you would need to make. Observe means you have to say what you would see. Even though you're not doing the lab, you would have to state what is it that you would see. All right, so then that was 2 marks. One to say that it's white QPT, and one to say why, the shift in equilibrium. This right here is also 2 marks. Let's do the math. Use the data to calculate the solubility of MgCO3. Oh, it's not even. This feels like the It's the same question. No, it's not. Same topic, though. Use the data in the table to calculate the solubility of MgCO3 in water. Is there a common ion in this question? No common ion. So how do I solve? Regular way. So regular way, this is as easy as the math can get. Sophia, Stefan, how's it going? Who's winning? Stefan's winning? Okay. Did you win or are you still playing?
Still in our first game.
But you're still in the first game.
Yes.
How long has it been since you started?
Don't forget to use the gallon.
What?
Don't forget to use the gallon.
Yeah.
Well, because pre-ace, I was gonna play something with pre-ace, but
I'll just say there's many loopholes to this.
there's many loopholes. Can you write them down?
Yeah, I have a critique.
Okay, you have a, okay, cool. Thank you. They're playtesting a game, so I can make alterations for pre-ace. So that, you know, they don't get stuck there for an hour trying to play a game and not figuring out what to do. All right, 0, 0. We don't know what this is, but we know we're subtracting x from it, right? So this means plus x plus x. Do you have to write out the ice table? Is there a mark for the ice table? There's not. You don't have to write out the ice table. If you understand, oh, this is going to be KSP equals x squared, you're fine. The ice table proves what it is. Now, what do we plug in? Perfect. Which comes from this table. So we plug in 1 times 10 to the negative 5 equals x squared. We take the square root. We take the square root. We get I did it already. 0.00316. You did the same. That's a mole dm minus a third. Is that my final answer?
No.
How many marks out of the 2 do you think I have right now?
1.
1.
It's right.
To get the second mark, what do I gotta do? Multiply by the molar mass. The molar mass of this is 84.3. So I multiply this by 84.3. And that gives me my final answer, which is 0.266 or 0.27. Minimum of 2 significant figures. Because BK is going to have 2 significant figures, is why. Okay, so as you're finishing writing that down, I was reflecting on whether or not to include this last part. I am because there are some questions in the textbook about it, and because it could show up on the Olympiad for those, practicing for that. But there is no standard that mentions this like in the current 2025 curriculum. So this is kind of an addendum. So I'm adding this to your notes. I could put a question about it on your desk. If I can find one. But year after year, I look for questions from Cambridge and I never see them on this topic. But it, like I said, there is at least one question in the textbook that goes over this. So just in an effort to cover every page, I am providing you with something a little bit extra. Here, this is something that looks like this. Here you go. 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 All right. So the last topic. Using KSP to predict if a precipitate will form. There is a concept that I never see Cambridge talk about, but if you were to take any chemistry class beyond here, it'll show up. And it's this concept of Q. And so I want you to write down that Q is non-equilibrium K. Meaning that whatever we have is not at equilibrium. So Q can be compared to K. So this means that we have concentrations that are not our equilibrium concentrations necessarily. And we can use this concept of Q with KSP to tell us whether we have precipitation or not. And so if you have concentrations of each of your ions, so we call that our Q, and it's the same thing as K. This means your solution is saturated, which means that you're not going to see a precipitate. You're just at equilibrium. You've dissolved everything. This means you've dissolved everything you can. You've dissolved everything. There's no excess. That's what that means. If Q is a smaller number than K, and I'll teach you how to calculate Q very shortly. But if Q is a smaller number than K, then you have not yet reached saturation. Your concentrations are not high enough. It has not reached saturation, which means that you could still add more. You can scan show and go. You can still add more of your compound and it will dissolve. And you will not see a precipitate. You won't see a precipitate here. You won't see a precipitate here. The only time you'll see a precipitate is if your Q, your concentrations for your anion and your cation, when you work it out, are more than K. Go ahead. This means that your solution is saturated, but that there's also excess of your compound. And because there is excess of your compound, you dissolved everything you can, and the extra must fall to the bottom as a precipitate. And so it will show as a precipitate. And so, like I said, I have seen questions in the textbook on this. You'll see it in the next slide. And that's why I wanted to go over this concept. And I was unsure if I wanted to show you the graph or not, but I think the graph could be helpful. That's why I printed this for you. Yes.
Okay, focus with Q.
I'm about to go over it with a practice example. So Q is your non-equilibrium concentrations. Q is your non-equilibrium concentrations. And it is the same method of finding Q is the same method of finding K. But Q may or may not be at equilibrium. So that's the difference between the two. Whereas K is equilibrium, Q may or may not be at equilibrium concentrations. So the situation, let's take a look. So this comes straight up from the textbook. This is the new textbook. So I wanted to make sure to address it. Check up 14B. Calcium sulfate is sparingly soluble. It could be made by mixing solutions that contain calcium ions and sulfate ions. I have a 0.00100 molarity solution of aqueous calcium chloride. And I mix it with a 0.001, so these numbers are pretty easy, molarity sodium sulfate. Question number 1. Calculate the concentration of the calcium and the sulfate ions when equal volumes are mixed. So they're basically saying you don't have to consider changing the concentration for the volume. You're mixing equal volumes. So how would I get, knowing that I have a 0.00100 mole Dn-3 CaSO4. The question is asking, how much is the concentration of Ca plus 2? Can you figure that out in this solution?
I think it's 0.00100 because there's only one C.
Right. Yes. So you don't have big brain. You don't have to math too hard here. The concept is there's one calcium. There's one calcium, which means the concentration should be the same. It's the same math I've been talking about with stoichiometry for a while. If you understand how proportions work, you're going to get it. So this equals 0.00100. Does that make sense? That is just the same. What about the sulfate? We have 0.0100, and they made this easy, like I said, Dn-3, Na2SO4. Wow, that is a weird S that I wrote. What is my concentration of sulfate here? Because this is the compound I'm looking to precipitate, or not. Because that's what they're asking. What is the concentration of the calcium? What is the concentration of the sulfate? So what's the concentration of the sulfate?
Okay, it's going to be the same thing.
Same thing. So when would there be some different concentration? When there's a subscript. And sulfate does not have a subscript because it's a polyatomic. There's no parentheses, which means I only have one. So that's our answer for part 1, is to calculate the concentrations of each of these ions in the solution that we're mixing together, that we made. And so now we're going to get to the actual question we asked, which is, will it precipitate form from this? That's the question. So the question is, and we'll have to go back to the slide to pick up these concentrations, will it precipitate form? In order to answer will it precipitate form, the first step is you have to find Q. Q is plug your current concentrations into the same equilibrium equation, understanding that that might not be equilibrium. So what does that mean? Well, what would the equilibrium equation for this be? Calcium sulfate. We have CaSO4. It's easy numbers, easy equation. What would it be? Welcome back. Yes. So I'm going to write it out here. KSP equals Da2 plus SO4 minus 2. Don't go with x squared. Why? Would these always have been the same? Would these numbers have always been the same? No, I could have made that 0.002 molarity, right? I could have made that 0.5 molarity. So it's better to write it this way. KSP equals the calcium ion concentration times the sulfate ion concentration. But now here's the change. Q equals this. So what's the difference? What am I even saying here? Because we don't know if it's equilibrium or not. We don't know if this mixture is at equilibrium or not. We just mix two things together. We want to see what that will give us. That's what Q represents. The math is actually the same to find Q as it would be to find K. But in other questions, we know that these were equilibrium amounts. Here we're just saying, I throw these two things together. Is it going to make a precipitate? Yes or no? You see the difference? Yes.
I don't get it.
You don't?
Aren't they always the same total?
No. Because Q addresses the situation. What if you were just mixed two things together? Will you be at equilibrium or not? Will you reach precipitation or not? You could have less in there than the amount needed to precipitate. That's what Q is addressing, is what do you have, not what is going to give you equilibrium concentrations. So put in the numbers. Maybe once the numbers are put in, it'll make a little more sense. So when you calculate Q, the actual numbers you would substitute would be to calculate Q. Once I've got the expression, we got to calculate what is Q. So this would be 0.00100, 0.00100, right? They happen to be the same because that's what the question gave us, easy numbers, but they wouldn't always be the same. You get Q equals, you plug in your calculator, 1 times 10 to the negative 6. So what you're supposed to do from here is compare Q to K, SP, to tell us if we are at equilibrium or not. Your Q number is 1 times 10 to the negative 6. That's what these concentrations that we put in solution gave us. What is your K according to the question? Q is 1 times 10 to the negative 6. K is not the same. It's 2 times 10 to the negative 5. This tells us how much we need to be at saturation, right? What this tells us is how much is at saturation. Have we reached saturation with that Q? We have not. Q is less than K. So what that means, Q is less than K. We have not reached saturation. If Q and K were always the same, that means that no matter what you do, you'd always get a precipitate. But that's not true. You won't always get a precipitate. You have to have enough of it to give a precipitate. We have not reached saturation. Another way of saying we have not reached saturation, we have not reached solubility, right? The full solubility of it. So will there be a precipitate if we have not reached saturation? If something's unsaturated, could I dissolve more? Yes. That means that I won't see any at the bottom. Back to all the way to Prius, right? So no PPT is the answer. No PPT. That's the answer to the question. The answer is no.
Wait, we don't have PPTs and we did reach saturation?
You did not reach saturation. Because this number was less than this number. So remember, it says here, if Q is less than K, we are unsaturated. There is no PPT. Our Q value, 10 to the negative 6, is less than 10 to the negative 5. It is less. It is not saturated. Yes? Pause, or am I good to try one more? All right. We have one more like this. Yeah, come on and came back, so yes, came back. All right, one more. Then review of unit 1. You see it's coming up. All right, will a precipitate form if we mix equal volumes of solutions of Na2CO3 and BaCl2? So what are we looking to try to do here? What are we looking to try to do here? What's the first step?
Write the equation out.
So last time it kind of led you to what you needed to do. The first thing you needed to do before starting was you needed to find what concentration of each of the ions that could precipitate are. So the first thing you should do here is find the concentration of barium and carbonate in the solution you're about to prepare, right? So how would I do that? Stefan, did you guys, and Sophia, did you finish your dispute?
Using the rules base.
No, I want the base of the technicality.
No.
Are you purple? Are you purple? What about you, June? Are you purple?
He asked if you're purple. I don't get it.
Oh, so you're purple, right?
Yes.
You
Go ahead.
like purple?
All right, I'll check in on y'all once I'm done with this question and see what that dispute is. All right, so find concentration of B plus 2 and CO3 minus 2. Does that make sense? I first have to know what the concentrations are in order to find Q. I can't find Q if I don't know what the concentrations are. So I need to find my concentration of barium. I need to find my concentration of carbonate. So how will I find barium?
It's the same one for
Because there's one here and we have that, it's the same. Just like last time. Do we have to write that out? Or are we okay with that? So we know that the barium 2 plus concentration is 5 times 10 to the negative 5. Is that all right? What is our concentration of carbonates? It's a 1, right? 1 to 1. So it would be 1.5 times 10 to the negative 4. Are we okay with that? That's our carbonate. After we find our concentration of each, we have to find Q, which means what?
You have to find both concentrations.
Find Q, which just means Q equals, take this and multiply by the same as the K expression. They're easy ones to do. This is one of each of them. So it'd be each to the first power, right? So then this would be 5 times 10 to the negative 5th multiplied by 1.5 times 10 to the negative 4. Q. I did the math. I got 7.5 times 10 to the negative 9. Let me know if that's what you get. So the $1 million question. Will there be a precipitate? How do we figure this out? 3. Compare Q to K. Like what we have mixed together. Compare it to what the equilibrium is. The equilibrium is, the Q is the same number, 7.5 times 10 to the negative 9. And K is 5.5 times 10 to the negative 10. Have we exceeded the solubility, yes or no? Q is more than K. We have exceeded the saturation or the solubility, however you want to say it. It's the same thing. Like we've exceeded the solubility, which means what? This means there will be precipitation. There will be precipitation. All right, so we are done with the core content for Unit 1. With that, we're done with Unit 1 in this class. We have finished most of acids and bases. There's a couple of things in organic chemistry we have to go over with what makes some compounds stronger acids or bases than others, but we will save that conversation until we revisit an organic because it's always good to go back and review the things we did before later on in the year. I have reasons. But in this curriculum, we are done with the chapter. We're done with the unit. There's also one other thing I am saving for organic called partition coefficients. Stefan, you remember those? Remember partition coefficients? Are they gross? Yeah. We'll save that for later in the year. But this is most of the core content for acids and bases. So let's go. So on Thursday's review, I wanted to mainly do practice activities. I'm creating some fun things for us to do, which I'm not going to say what it is until Thursday.
Wow.
But you'll have to put your thinking critical skills hat on Thursday after the bell. But let's go ahead and review the formulas that we've used and when to apply each one right now, because that's where, when you're studying for the test, where you're gonna have a possible issue, is knowing when to do what? Because you're just gonna get a question, calculate the pH. How do you know which method to take? So, what was the first scenario that we had? Strong acids and strong bases. So the first scenario is they give you a strong acid or a strong base. Will they tell you that in the question? For strong acids, they definitely won't. For strong bases, it depends. Because, for example, if they give you barium hydroxide, I've seen it in questions, they'll have to shout out that it is a strong base. But the strength of hydroxides, remember, their solubility increases as we go down the group. So calcium hydroxide has a K to it, but barium does not. So when you get into this section, they'll usually specify to you whether it's a strong base or not. But what I told you have to remember for bases is that group 1 bases are definitely strong. Go ahead. So strong acids or strong bases. You need to memorize what they are. The strong acids, what are they again? We're going to keep repeating them. HCl, HNO3, and by name. You have to know them both by formula and by name. Because it could be provided either way. And sulfuric. Those are your strong acids. And if you're given any other acid besides those, you would be given a Ka along with it, right? Because it will be weak. So if they don't give you a K, they don't ask for Ka, and you have one of these, and this is my strong acid. So what are my strong bases? Like, what are the ones you have to know for sure, that you are responsible for knowing for sure?
All right.
Group 1 hydroxides. Those I'm pretty sure Cambridge will not specify to you that they are strong. I've seen a bunch of questions and they basically assume that you're supposed to know if I give you NaOH, that's strong. So group 1 hydroxides. Okay, so what are we supposed to do to calculate pH? We have to know our formulas. pH is negative log, H plus concentration. What other formulas did we have? Go ahead, Ramon.
What's it called? Negative log OH, 14 minus negative log OH. Technically.
Go ahead, Alexander.
I think what Ramon meant to say is 14 minus POH.
Oh, well, you're saying pH plus POH equals 14. Like the two scales always add up to become 14.
Yeah.
So if you have one, you can easily find the other by doing 14 minus 1, and that'll give you the other. Yes. Okay.
The concentration of hydrogen ions times the concentration of hydroxide ions, it's equal to 10 minus negative 1.
This one. Kw is H plus times OH minus. At 25 degrees Celsius, that would be 1.0 times 10 to the negative 14. Can we always assume 25 degrees Celsius? No, because you could get a question where they vary the temperature. I gave you some examples like that. And then you had to solve for what is the new Kw or the new pH. Yes.
pH equals pKa plus negative log.
Not for strong acids. That's for something else. That's why I said we gotta go over when do we do what. What else can we use for strong acids and strong bases?
The concentration of hydrogen ions is equal to 10 minus to the negative pH.
Yes. Concentration of H plus is 10 to the negative pH. That's a big one. Because if they give you the pH and they want the H plus ions, this is your method to get there. And there was another one here. I'm going to put a slash. POH equals negative log OH minus, right? And here, OH minus would be 10 to the negative POH. So if I swap out POH for pH, instead of finding the H plus, I'll find the OH minus. Which of these formulas are allowed but actually not mentioned by Cambridge? And I believe I gave you homework questions where it even said in the mark sheet, you're allowed to use this as an answer, but it wasn't the initial method that they used to solve. Go ahead. POH. So POH is not required to be learned. for this class. You can technically solve everything with this formula, and that formula. Just those three. You can solve everything. However, the math might require more than one step. So the POH is kind of like a bypass to make some of your math easier. And so it is up to you whether you decide to use POH or not in your calculations. You won't be counted wrong if you do, as long as your chemistry is correct. All right, so that's strong acids and strong bases. We use these formulas for that. We brought these formulas up first in previous chemistry. Then in AS chemistry, we never needed them. So we never looked at them again. And now we're back on these formulas. All right, that was situation 1. What's situation 2? What if I have a weak acid? So how do I know I have a weak acid in a question? Cambridge will likely not tell you. I mean, it's not impossible. But usually they will not tell you have a weak acid. They'll be like, what is the pH of a 1 molarity HF solution, Ka equals blah, blah, blah. That's all.
I think that if it's not one of the strong acids, you're supposed to assume.
You
that
must
it's weak,
assume weak.
unless they say otherwise.
Yes. So assume, if not, one of the strong acids. And what is another clue we could have? That is a wonderful response. Organic acids are weak. That means carboxylic acids, right? And what is another way that we could like reason out that we have a weak acid, Francesca? If they give you a Ka. If a Ka is included, absolutely. If a Ka is included in the question, you have something weak. Don't go directly to these formulas or you are not getting marks. Because there's something else you have to do first. So Ka is referenced. Either it's provided or it's asked for. The fact that they've referenced Ka at some point is telling you, hey guys, you have a weak acid around. So what do? What's the strategy? Go ahead.
You use the Ka formula.
So there's a Ka formula.
Uh,
Ka equals H plus times X minus over HX, I believe is how I brought it up. And in this formula, because of the way that the equilibrium is, what can you always assume? If you do the ice table, it proves it. What can you always assume? These two are the same as each other. So you can technically call it x squared over hx, as long as you understand that when you're solving for the small x, that it is your H plus concentration in this formula. Ring a bell? Question? No. So this was our second method. These questions are worth 1 or 2 marks. They're not worth a lot. But you have to recognize when to do what. Like I said, that will be the most difficult thing in the first unit exam, is recognizing which of the formulas you have to use. It's memorizing them, but then knowing which one. Because if you choose the wrong one, you're going to get the wrong answer. We have other things we learned. This is just the first week, right? The first things we learned. What was the next major topic that we had? Go ahead, Issa. Buffers. So situation number 3 is we have a buffer. And how do we know we have a buffer?
As a strong acid and it's not a weak acid and it's conjugate.
So buffer solution. They may reference in the question, you have a buffer. They may not. If they don't mention you have a buffer, then they're either giving you one of the following 2 scenarios. They're either provided with concentrations of weak acid and conjugate base, which can show up as an ionic compound, which we call a salt, right? And what is the other way they could have you make a buffer? These are mold table, but how could they, what would they be saying we're putting together? to say that you have to do that, because they're not gonna say, hey, make a mole table to solve this. Francesca,
Or ask for the pH of those.
but they'll always ask for pH. Go ahead.
Okay, two ideas. Either they ask for the pH of the buffer, or
But they don't say the word buffer.
and then the second one would be if you have a weak acid, you mix it with a strong base.
So
and-
weak acid mixed with a strong base, which creates the conjugate base, right? And to solve that, you would need a mole table, or whatever way you want to find the moles. That, like, it's a limiting reagent question at that point, and you have to figure out how much of each of the reactants you use to get your product. I gave a practice set on Friday with a bunch of questions. I know that it was a little bit frustrating, but the whole point of that exercise was to practice, because you need to practice making those mole tables to get better at it and faster at it. What's the formula for buffer? So formulas for buffer. So you've got that situation, one of those situations occurring. What's our formulas? And how many do you have to memorize for buffer? You just pick one. Francesca.
H plus equals is K thing
It's H plus equals,
or K?
either you can call it ask, acid over salt times Ka, or you could do H plus, the same exact formula, acid over conjugate base times Ka. But understanding that this is the weak acid, not strong, and this is a conjugate base, not strong base. So it's either ASK or APK, your choice. That's why when I was taking analytical chemistry courses, they would always call it the salt that I remember. But sometimes the salt is not observed. Sometimes you don't see the other ion there, and so you might get confused. And so that's where conjugate base comes into play. All right, that's the one variant of the formula. What's the other variant? Which is literally the same thing, just algebraically manipulated with logarithms, Ramon.
pH is equal to the pKa minus plus log of acid salt over acid.
Salt over acid or base over acid. Either way again. Remember, salt and base, conjugate base, can be used for each other. So this would be salt over acid or base over acid, right? And that's a log 10. So standard log. Adds up.
On the test, are we going to be given like a giant table with a bunch of values like with our assignment?
What do you mean?
Like, are we going to need to know the pKa's of like a set?
Oh, no. They're not gonna. So they'll either write the Ka or pKa directly into the question, like in parentheses in the question, or they'll present it in this manner.
Okay.
Not a gigantic table, but it could be a small table. But it won't be like that science geek where you had this gigantic table that you had to sift through. It'll either be like something small like this, or it'll be directly into the question. Under no means do you need to memorize KAs or KSPs. Those would be provided for you. But what you do need to memorize is these, this, one of these, right? The buffer. And so that was buffer. And so we spent 2 class periods going over buffers. And then we just spent 2 class periods going over KSP, which is our final major topic on this test. So what's KSP? So this is solubility product, which at its bare essence is KSP equals products. That's why it's called solubility products. And what you're supposed to do is when you make your equation, so let's say that you had CaOH2, which does show up as a solid, you would get this. And what would this become? your KSP expression would be CA plus 2, OH minus to what exponent? To the second. And then what else are you supposed to do? To do the math, you would call these 0. And when's the only time you don't call these 0? Not 0 if, we learned today, common ion present. Then you have to put in the actual initial concentration, plus X, plus 2X. Then you plug the values into your KSP formula to solve. And it gives you an equation, and you either have to solve for X, which is solubility, welcome back, or you have to solve for KSP. So the only two things you'll be asked for here is either solubility or KSP. Those are the two things that you could be asked to solve for. So in this one, you would get KSP equals X, 2X squared, and then so it's 4X with a third, and that's how you will solve this specific question. X is for solubility, and KSP is the solubility product. All right, so we are done with Unit 1. You actually have time to work on your homework. How amazing is that? Because you're all so good and you ask good questions and we move through the lesson. You have time to work on your homework for lesson 6. Go ahead and take out your workbooks, and you've got about 20 minutes to work on your homework for common ion, which the first page is actually just regular KSP questions. So go ahead and get started. This homework is due Thursday morning. So utilize your time wisely. I'm going to do two things. I'm going to put out the electric, I think, let me double check if we're done. Doesn't say. Okay, we can see it.
Lunch.
We got to help professor. There's nothing to do.
All right, I was doing this. Okay. You want to see my funny video in the calculator? Can I clear this for a second? Thank you. 6, 7.
That's one.
What about me?
You just do
Oh, yeah, whatever you said I did do.
Oh, I don't care.
You draw this, at least you're better. Duck E3. Here, you got this now.
So there are not going to be like. What is your opinion? What's it called? Okay, so I think that was you. You want the game?
Not yet. I want this. What's for
Okay, so right on the board, the first one say like that's supposed to be right? I don't know. No, but that's not. The point is, you like your donuts anyway, so completing it, that it.
Anything is
Sophia's going.
Uh,
Back.
there you go.
Sophia, when you come back, somebody else has to go. All right, I can start recording. Why am I still recording? All right.